Hi everyone, today I'm going to present our work, Data Augmentation for Object Detection via Controllable Diffusion Models. So our motivation is for image classification. There are a few works using clip and diffusion models to create synthetic training data to boost the model's performance when there's data scarcity. So can we perform generative data augmentation for object detection without additional human annotations? And also, due to the intrinsic feature of the bounding box label for object detection task, the generation process requires more fine-grained control. So we propose an augmentation pipeline using controllable diffusion models. The input is input are some real images and their annotations. And we first do some regular data transforms like random crop, resize, flip, etc. And we got the processed image, and we use a vero prior generator to extract the vero prior. So the vero prior could be canny edge, head edge, or semantic mask, or scribbles, etc. And then we construct a text prompt, which basically describe what's in the image. And that's from the ground truth annotation. And then we input the text prompt and the vero prior into the controllable diffusion models and generate synthetic data with images and also the annotations. And then we calculate the category-calibrated clip rank for each bounding box. So here for party plan, for table, and for sofa, we have different score thresholds. And in post-filtering, we filter out say here we filter out 70% of the data and keep only 30% of the data, and we use post-filtered data as our synthetic training set. So our main result, first one is on COCO dataset few shot strategy, and we show that on ULOX small, we compare with the stable diffusion in painting and also another in painting algorithm called paint by example. We show that our approach outperforms baseline methods by a large margin on the 5-shot, 10-shot, and 30 shots. And also for the large transformer-based dyno swing large detector, we also show that our data augmentation performs better than baseline on 5-shot and 10-shot and on par on the 30-shot. And we also test our model on ULOX small detector on the full PASCAL VOC dataset, and we have significant improvements on all 6 metrics. And for MAP, we increase the MAP from 52.5 to 53.7. That's a 1.2 MAP increase on VOC dataset. And we also have some takeaways apart from the main results. The first one is post-filtering is necessary. So here we test for no filters, where we keep 50%, 30%, 20%, and 10% of the data. And we see that for 30% it works the best, and also if we keep 50% data, it also works well. But for no filtering, there's the result is below, and also if we keep too less data, like 10% of synthetic data, the MAP, the result is the performance is really low. So a good point for post-filtering is it can filter out the irrelevant data, which is noise signals generated by generative models. But if we use the filter ratio which is too high, there will be a heavy distribution shift, because some images they can just generate good synthetic images. And if we use a 10%, say if we keep only 10% of the data, there might be some images that has no synthetic augmentations. And we also show that our works work well with other augmentations. So we test on ULOX small and also dyno swing large. So we show that we even both with and without original augmentations, our augmentation pipeline can improve the model's performance, and especially when we have the original augmentation, and both the original augmentation and our augmentation, the model works the best. And we also show that our works better within painting. So we use the paint by example in painting algorithm. So we show that if we keep a small portion of the synthetic data from paint by example and a large portion of data generated by our model with high visual prior, and we plus 30% of post-filtering, the detector works the best. So both this one and the last page shows that our approach has good synergy with other data augmentation methods. And the last one is to choose a good visual prior. So for those four visual priors, candy edge, head edge, uniform segmentation mask, and scribble, the control is from fine to coarse, and we see that for head edge visual prior and uniform or mask, the model works the best. This is because when we have the control that is too fine, it might contain too much details, and there will be a lot of noisy signals in the synthetic data. And if we use a control like scribble that is too coarse, the model will the image will lose a lot of edges or details, and it will confuse the controllable diffusion models to generate high quality data.